Welcome to the CPCI webinar on the design of Hollowcore diaphragms. Today's webinar will provide an overview of the behavior and design of precast concrete floor and roof diaphragms. Our presenter today is Wayne Kassian from Kassian Dyck Associates. Wayne is experienced in precast concrete design and is a member of CSA's Technical Committee for Reinforced Concrete Design in Canada and the Canadian Precast Concrete Standard, as well as serving on various technical committees, including PCI's, TAC, BIM, and Architectural Precast Committees, and the CPCI Precast Prestressed Technical Committee. Wayne also serves as the director of the Accredited Certification Organization for the CPCI Precast Concrete Certification Program, qualifying precast plants across Canada. The webinar will be about an hour and 15 minutes in length. Participants are muted from the discussion, but are certainly welcome to type in any questions and comments in the Q&A box that is on your screen. These will be answered at the end of the presentation.
Thank you for attending this webinar. I'm Wayne Kassian from Kassian Dyck Associates, consulting engineers in Calgary, Alberta, and today we're going to be talking about Hollowcore diaphragms. So in this webinar, we're going to be discussing the purpose of Hollowcore diaphragms, diaphragm behavior, looking at different components in the diaphragm, diaphragm analysis, code requirements, how to handle large openings and look at force paths, and lessons learned from past earthquakes. So the purpose of a diaphragm, it's part of the structural system, and it's an element that transmits lateral loads such as wind or seismic loads to the vertical resisting elements of a structure. So within a total precast building or other types of structures, it's the hollow core, as shown in this example, that is the floor plate diaphragm, resisting lateral loads, transferring those lateral loads to the precast shear walls. So basically, diaphragms are that horizontal floor or roof plate component, which is an important aspect of structural design that is used to transfer the lateral forces to the lateral load resisting system. It's typically used in total precast structures where hollow cores form floor and roof assemblies and are used to transfer loads to the shear walls or cores, and can be used in other type of structures as well. Again, the Hollowcore floor system is designed as a diaphragm beam to transfer the loads to the lateral load resisting system. Hollowcore works well with the long span to depth ratios as a pre-stressed precast concrete element. You can have long spans with a shallow structure, and you can open up your structure with beams that are integral with the floor slab system to have nice wide open spaces within your buildings, as shown in these photos. So really the Hollowcore in these examples is acting as a lateral system where the wind and earthquake loads are being transferred to the Hollowcore floor and roof, and then the Hollowcore acts as a system to transfer loads to the shear walls or core walls that are being used to resist lateral loads. Precast pre-stressed concrete offers many advantages. The larger span to depth ratios allow for larger open areas in buildings and parking garages due to the long span capabilities while keeping member depth shallow. As a pre-manufactured modular system of construction with pre-stressing, you get enhanced performance with less material usage due to precast concrete's high strength, as it's designed to be efficient and economical. You can begin casting components for the superstructure off-site while foundation work is in progress, leading to an accelerated construction schedule. You also get the benefits of construction speed due to precast concrete's ability to erect the superstructure quickly all year round, so the project can avoid delays due to waiting for concrete to cure on site or delays caused by harsh weather. The National Building Code of Canada, provincial codes, Canada's concrete and precast standards require precasters undertaking work on buildings in Canada are properly pre-qualified as a manufacturer, and CPCI members are certified through the CPCQA certification program, formerly known as CPCI certification. Precasting concrete in certified plants ensures manufacturers are capable of conforming to the required standards in order to produce high-quality architectural and structural products. With precast concrete, you also get the benefits of improved quality control by constructing elements in plant-controlled conditions that provide increased reliability of construction. In fact, that's recognized in the Canadian Concrete Design Standard CSAA 23.3, where designers can take advantage of the increased strength capacities of precast concrete as compared to cast-in-place concrete construction. Precast concrete is non-combustible and does not require additional fire protection, and this can result in reduced insurance premiums both during construction and in service. Precast is durable, providing a long service life, and its inherent resiliency due to its mass and high strength can provide protection from earthquake, tornadoes, hurricanes, and even blast loads. Precast provides excellent thermal and acoustical control, providing pleasant work and living conditions for users and inhabitants. On the project site, precast concrete construction minimizes site impact by casting precast components off-site and can make use of just-in-time delivery with small erection crews as compared to other systems. That reduces the number of personnel and trades on site, which reduces safety and other risks at the job site. And of course, don't forget, precast concrete provides aesthetic versatility where you can get a variety of shapes, textures, colors, and finishes that provide a really nice looking and durable structure. So as you can see, there are many advantages with precast pre-stressed concrete construction. So with Hollowcore diaphragms, again, we mentioned in any type of structure, they're going to be that horizontal floor roof component that's transferring the lateral loads to the lateral load resisting system. What we're talking about today can be applied to other types of structures where, double T's or other types of floor members are used as diaphragms as well. So a lot of what we're going to be discussing today are basic principles that could be applied to other types of structures as well. The purpose of diaphragms, so diaphragms are one component in that complete load path where we look at, okay, we have a wind or seismic load, it's going to have to go through various components or connections down, eventually reaching the ground and being transferred into the foundations and the soil. And the diaphragm design is just one link of that load path. It's the important one that transfers the lateral loads to the vertical load resisting system, and we have to ensure that that's properly checked as structural engineers. If we don't properly look at the diaphragm or the diaphragm connections, then our load path could be broken, and as structural engineers, it's our duty to follow the loads through from where they're applied down to the final reaction to ensure that we have a complete load path for the safety of the structure, and that requires proper engineering effort. Additionally, diaphragms resist gravity loads. Obviously, hollow core, if it's your floor system, it's going to have to support your floor loads in addition to working as a lateral diaphragm. A lot of architects today are potentially having inclined columns on structures, which create horizontal forces due to the thrust from the sloped columns. If you have a diaphragm at a main floor with a structure that's below grade, the earth pressures pushing on the walls may have to be transferred through the diaphragm to the lateral load resisting system. And obviously diaphragms are used to tie the whole structure together. So if we look at this diagram, we can see, obviously the diaphragm has to resist gravity loads. It has to be acting as that horizontal plate beam type system. In this case, we're also showing a diagonal column that's creating a thrust onto the diaphragm. You can also get that type of thrust on a long wall where you have a vertical point load coming down at one end of a wall, and then if you're transferring that load through kind of a transfer wall to another location or a transfer column, then if the reaction above is not in line with the reaction below, you can end up with a horizontal thrust as well. So you don't need a sloped or diagonal column to generate that diagonal thrust. You could also have that just with an offset vertical load where the load coming down from above is not in line with the resultant load below, and that can also cause a horizontal thrust that you need to design for. And then certainly with any diaphragms that are resisting soil pressure, you need to look at that as well as a design engineer. So now we'll just talk about some overall diaphragm behavior. Diaphragms are typically thought of as a horizontal plate type beam where you're transferring moments and shears to your shear walls or shear wall cores. So it's basically acting as a big horizontal beam as shown in this plan view looking down on a hollow core or double T type framing system where you're going to use that floor to act as a beam and transfer the loads to the shear walls on each side of the structure. So with earthquake force, we typically can look at what's happening as far as the behavior of the diaphragm by lumping the resultant earthquake force at the center of mass of that particular floor. In this case, we have a symmetrical floor. The center of mass is in the middle, so we can think conceptually of the earthquake force applied at the center of mass. And if we have a shear wall off to the left-hand side, which is where our resistance is, we see the two are not in line. And when that happens, we're going to end up having a resultant torsion because the force that's being applied as a earthquake force in the middle of the building, the shear wall is off-centered, it's eccentric to that force, so we get this twisting torsion caused by the earthquake load. If we had a structure where we have 4 well-distributed cores, that provides good torsional resistance. So when we have that load applied at the middle of the diaphragm at the center of mass, we have a good system to resist that load without causing torsion and or having reaction points that can suitably resist the torsion. However, if you were dealing with buildings where all the cores are off to one side and your center of mass is still near the middle of the building, you can see that the center of resistance is skewed quite far from the center of the mass. That would develop a large torsional force during an earthquake, and also as shown on the right-hand side, if you just had shear walls on 2 sides, that's certainly not a good system for resisting torsion where you've got a center of mass in the middle with the earthquake load being applied there. That would not be a very good system as far as torsional resistance. So just overall looking at buildings, if we have a core, smaller core in the middle, that's not going to be great for torsion. If we had shear walls on all 4 sides towards the outsides of the building, that would provide good torsional resistance. On the bottom left, 2 sides having shear walls, again, that is not good for torsional resistance. And if we just had shear walls formed like an X shape near the middle of a building, again, that has almost no torsional resistance also. And you really need to investigate and look at triangular buildings and their behavior because they require special consideration. So if we think of a diaphragm as a beam turned on its side, so we know that beams typically need flanges to assist with improving their strength and resisting bending. So a diaphragm is no different. We would like flanges to have some capacity to assist with the bending. And if we had a beam and we cut a notch in the flange, we would intuitively think, well, that's going to have to be investigated because we've reduced the capacity of that beam by notching out the flange, and we're going to have to design appropriate strengthening and stiffening to still carry the loads in that beam because we've affected its structural capacity. And hollow core is no different. It's beams turned on their side, and if the perimeter of our beam is going in and out due to balconies or other requirements for the building structure, we have to consider those as notches in our diaphragm beam and do design appropriately. So when we have diaphragms as a horizontal beam, we really need to look at what's happening at any notches and penetrations, just as we would with any structural beam. And then we also need to make sure that we're adequately connecting the diaphragms to the lateral load resisting system, the vertical elements that are then going to transfer the lateral loads down to the foundation. So in addition to looking at how the Hollowcore diaphragm is connected to vertical members, we also need to consider interstory deformations, where during an earthquake, the floors above are swaying compared to the floor below, and you're getting differential deformations, and your stairs need to be able to go along with that movement. If they're rigidly connected each end, they're going to attract loads into them, and if they have, you know, a slotted connection at one end that would permit movement, then they're not going to attract any force. But if you don't consider those interstory deformations during an earthquake, if the deformations is large, you could lose support at the end of a stairway, and you know, you don't want to do that because occupants need the stairwells to get out of structures in an extreme event. So you do need to look at even, you know, your stair detailing and ledges to ensure that they have adequate capacity for going along for the seismic drift during an earthquake. So we know if we have a diagonal brace in a structure, that becomes part of the lateral load resisting system. The lateral loads are going into that brace, in this case a steel brace with a building utilizing hollow core floors. But the same happens when we have precast stairs. They're going to potentially act as a brace member because they're on that diagonal. So if they're there, they're potentially going to attract load if they're connected top and bottom. If one end is released, then they may be able to move and not attract load going through the stairs as a brace, but it's something you need to consider as a structural engineer. And also, you know, in parking garages where you have sloped floor plates that are acting as ramps, those can attract lateral load as well because they're a huge potentially braced element that is on a diagonal that can attract lateral load. So that all needs to be considered with the structural design. Now we'll discuss diaphragm components. CSA A23.3, the Canadian design standard, talks about various diaphragm components. Chords, which are the flange reinforcing in the horizontal diaphragm beam, are proportioned to resist, you know, tension and compression as a result of the bending of the beam. And collectors are used to transfer forces from the diaphragm to the various components of the seismic force resisting system. CSA A23.3 also talks about shear panels, which is a shear plate, a portion of a diaphragm that is required to transfer forces as part of a component of a diaphragm, and also looking at an analysis that might involve a strut-and-tie type approach. And we'll discuss both of those in this webinar. So if we're looking at diaphragm components, this is a building where we have shear walls. The lateral load resisting system is on the left and right sides, and we also have one in the middle. We're going to look at that as a big floor plate diaphragm acting as a beam, transferring loads to those shear walls. So when it's acting as a beam, we know if the load is coming down as shown in this diagram, although seismic load and wind load can obviously act in both directions, but we would expect if we're spanning from end to end for the force to develop as compression and tension due to the bending. And then we also have collectors that are used on each side that we're going to drag the diaphragm forces into the lateral load resisting shear walls. When we have load being applied in the perpendicular direction, we now have a very, very stiff beam with the same components of the diaphragm. We now have compression and tension zones on our diaphragm, which would be happening in the chord regions. And again, we have to consider collectors that are going to drag the resultant shears from that large diaphragm back into the shear walls. So if we're using that entire floor plate as a very stiff, rigid beam, and we're counting on the strength of the whole floor plate, then we're going to have to use collectors to get the shears from those regions back into the shear walls. So in this case, we have a building with a long shear wall completely connected to the diaphragm. So with our shear load, we can have nice connections all the way along the shear wall, connecting the diaphragm to the shear wall directly. In this case, we now have a shear wall only being a partial length of the diaphragm. So we're going to have to look at how load from that diaphragm is going to get into that smaller length shear wall. So if we're designing the entire 3-bay diaphragm for strength and we have shear in the entire diaphragm, then when it gets to the support, we're going to have to transfer those loads back to the shear wall. So we're going to use a collector element to drag those forces to the shear wall. Some people might call that a drag strut, but it's really transferring the forces from other regions of the diaphragm to your shear wall, and you're going to have to come up with an analysis, a load path whereby you can get those loads properly transferred to the shear wall. In precast pre-stress design, we do a similar thing with dapped ends of beams, where on a beam we might have our main shear coming in a full depth member, and then right at the support we have to transfer the load to another location. So we would use hanger reinforcement to drag that shear, drag that total shear force up and over into the reaction point. So that's essentially what we're doing with those collector elements. We can think of it in the same way that we're transferring that entire shear load up to where our reaction point is, and we just need a structural model that we can follow that force path and check the strength of those components for the required loads. So the traditional diaphragm approach is to look at a diaphragm as a horizontal beam with uniform lateral load from wind or earthquake applied to it, spanning between two supports. And what we can do is analyze that as a beam made up of various components, look at the shear flow between them, design for the compression tension for bending, design for the shear, and come up with a system using this analogy kind of as a flexible beam type approach, where we believe the diaphragm is acting as a beam. And that's sort of a traditional analysis approach that might be appropriate in some circumstances, and we may use that to transfer the Hollowcore diaphragm forces to the precast load-bearing shear walls as shown in the photos. Again, it really depends on the geometry of the building and the dimensions of the diaphragm, if you feel that type of approach is valid for your particular structure. So what we're trying to do again is look at that component system made up of Hollowcore or other precast components that are forming the diaphragm and transfer those loads through to our shear walls or our elevator stairwell cores that are acting as part of the lateral load resisting system. So diaphragm analysis comes from the National Building Code or provincial codes, CSA A23.3, the design of concrete structures. The next version of CSA A23.3 that is coming out in 2019 is actually having some changes. They are replacing the traditional clause 19 for shells and folded plates with a new clause devoted to diaphragm design, which will apply to all types of structures. And then clause 21 for seismic will include additional requirements for earthquake design, but the new CSA A23.3 coming out in 2019 will have a clause devoted entirely to diaphragms. Other references that are good for looking at diaphragm analysis include the CPCI design manual. That's available from the cpci.ca website, and also PCI's manual for the design of hollow core slabs and walls, and also for American design, but it's a good reference as well, has some good information, PCI's design handbook. So with respect to diaphragm analysis, if it's a rigid diaphragm, so in this case, if we have a beam spanning between two supports and we look at it and say, wow, that's a really small aspect ratio. It's a nice stiff member. It's very deep for its span. To us, it's looking like it's going to probably behave as a rigid diaphragm. Kind of rule of thumb from ASCE 7, which is an American standard, but provides some guidance, is span to depth ratios less than 3 could be considered rigid diaphragms and having no horizontal irregularities. However, with a parking garage, we have to remember that if the center bay was sloped, then it would not be in line with the diaphragm on the adjacent bays. So that may turn our structure from a rigid diaphragm into potentially a flexible diaphragm, because we no longer have one overall stiff beam. We've now broken that up with this kind of opening due to the sloped ramp region in the center of the parking garage that can change the behavior of the diaphragm. So if a diaphragm is totally rigid, we know from structural theory that if we apply a uniform load or a lateral load to that diaphragm and it's fully rigid, then it's all going to move rigidly. And if our shear walls all have equal stiffness, in other words, they're the same length and they're the same height potentially as a cantilever, we know for cantilevers subject to a point load at a given height that their deflection will be a function of, the load times their height cubed divided by 3EI. Just from structural theory, PL cubed over 3EI, we know that, well, the force in all of those shear walls would be the same because they all went through the same deformation, the same deflection. So in that case, we know that the load on each shear wall with a totally rigid diaphragm, if it's a rigid plate and it moved that whole floor system uniformly, then we know the load in each of the shear walls is equal, and we would design the diaphragm as a rigid plate, and we would undertake to design differently than if that system was a flexible beam. So with a flexible diaphragm, ASCE 7 indicates the span to depth ratio would be greater than 3. It would potentially have horizontal irregularities, and also looking at the in-plane deflection between the shear walls being more than twice the average story drift. So those guidelines are provided in ASCE 7. So for that type of flexible diaphragm behavior, now instead of being a rigid plate that's moving, we're now applying our lateral load, and we're getting bending and flexure more like a two-span continuous beam. So it's a different type of behavior, and we know from a two-span continuous beam, the reactions on the supports under uniform load are not equal. The end reactions in this type of case, if it was a flexible beam following beam theory, would be 0.375 WL, whereas the center reaction would be 1.25 WL. So you get different reactions in the shear walls, quite substantially different with flexible beam type behavior as compared to rigid behavior. So you really need to look at both when you're designing your structures and determine, is it a rigid diaphragm or is it flexible, because you get different moments and different shears which will affect your diaphragm design and affect your shear wall design depending if the diaphragm is acting rigidly or flexible. So unless a diaphragm can be idealized as either flexible or rigid, you may have to consider that it's a semi-rigid diaphragm, and guidance is given in ASCE 7. So if you don't know if it's flexible or rigid, you may have to do a boundary envelope design looking at the effects of both. You may have to do a more precise analysis, and it's been shown that, even that aspect ratio of 3 may not necessarily be sufficient. So you really need to analyze your structure and be looking at what's happening. Is it rigid? Is it flexible? Or do you have to look at, could it be somewhere in between where you need to do a boundary envelope design? Now we'll discuss diaphragm design and code requirements. So with respect to designing the diaphragms, we have the simple horizontal beam analogy, or we could look at strut and tie or kind of truss approach with respect to how we're transferring diaphragm loads through the diaphragm to the shear walls. So the horizontal beam analogy is similar to a beam where you have a load, you're going to span between two supports. So in our case with the diaphragm, it's a horizontal beam still spanning between supports, which would be the shear walls. So with topped hollow core, we could look at the floor diaphragm as a horizontal beam. And when I'm talking about topping, I'm mentioning, 65, 75 millimeter thick reinforced concrete topping that's acting as part of the diaphragm, not just a little floor leveler that's put in. So in this case, it would be the actual concrete that's contributing significantly to the diaphragm behavior with the reinforcement in the concrete. So with the top system, we could look at this as a horizontal, continuous, monolithic beam spanning between supports. In this case, it's a two-span beam, two-span continuous. So in this case, we would design the web of the beam to take the shear and the chords taking the compression or tension from bending, just following a traditional horizontal beam approach. So depending on whether diaphragms are topped or untopped changes our approach. So if the hollow core is topped with a concrete topping that's reinforced and the topping is providing the diaphragm, again, we have a nice monolithic concrete beam that we can design, make sure it's okay for shear and moment, and design the diaphragm beam accordingly. However, with untopped hollow core, we know our beam would be made up of various components, such as hollow core or double T's, and these are individual components that are making up our beam. And we would know under load, wow, if we've got a beam made up of all these individual components, that's not going to work well unless we connect them together. And these type of elements are what we had referred to as sort of shear panels, where we've got individual pieces of that beam and we're going to have to connect it together to act as a beam. So with hollow core, that means we really carefully, if it's untopped, need to look at the connections to make sure it's all acting as a large overall diaphragm beam. So with untopped hollow core, we have a diaphragm made up of various hollow core planks. Again, looking at a system where it's two spans under a certain depth. So we can analyze this system where the chords at each end of the diaphragm are taking the compression and tension, and then we need to look at the hollow core joints between each of the elements, how that is resisting shear and transferring shear to the supports. So we're going to have, in this case, with the load coming this direction, we're going to design chords sufficient for compression on one side and tension on the other, and know that there's load reversal. So we're going to have to look at that in both directions. And then we're going to have to look at that shear and shear flow between the individual hollow core planks and follow those forces through to transfer them to our shear walls. With sort of the strut and tie or truss approach, just based on the aspect ratio and the design of the diaphragms, again, we could maybe look at coming up with a truss approach to examine how are we transferring those lateral forces through a diaphragm that's idealized as a truss and following the forces through the particular truss members to get to the support. So in that case, we're designing axial members, regions within the diaphragm to properly transmit the loads. Chord reinforcement that may be required at the ends of the diaphragm could be placed potentially, within the wall region or the end of the floor region, and really needs careful examination. The detail on the left, which shows, chord reinforcement cut into the hollow core, may not be a preferred solution by some precast engineers and precast manufacturers, and you may want to look at putting that chord region in zones that are, at the wall at the end of the hollow core. And you really, as long as you follow the forces through from where your chord reinforcement is and how it's getting there, look at shear flow, look at the location of where your actual reinforcing is and how it's being transferred there. You can provide that reinforcement in various zones at the end of the diaphragm, whether they're within the hollow core plank or within the wall system, but really looking at how you tie that together is very important as far as following the force path through. So again, in these examples, potentially the chord reinforcement is located in the masonry or other types of walls, and you just need to follow the forces through, look at the shear flow, follow the path such that the chord reinforcement, if it's not within the plane of the hollow core, is properly reinforced, that you can transfer and get the required compression and tension to those elements. On the cpci.ca website, there are various documents available that show some typical details. So connecting hollow core planks together without a topping is very important. We need to take all these individual planks and make sure they're connected together to act as an overall plate beam. So with respect to connecting hollow core planks together, this particular detail is used in Ontario, whereby U-shaped bars are put into the joints to tie the hollow core pieces together to provide some type of shear flow connection. And with a keyway, as shown in the bottom right, that gets grouted in, so you have a certain portion of keyway there that could potentially provide a little bit of shear resistance as well through shear through the grout. But you have to remember that that entire depth of hollow core is not grouted. Really, the grout is placed from top and goes down into the shear key. So if you were relying on any resistance in shear of that grout in the keyway, the area, the perimeter that would possibly be providing some sort of shear bond is really just in that keyway area, not the full height of the hollow core. But obviously mechanical connections like are shown and designed by the precast engineers are used for that shear flow as well. So again, just some examples looking at how you have to connect the hollow core planks together to act as the diaphragm, and also connections to the walls and the lateral load resisting system are important. And again, just showing some concept details of different connections out of some publications that are available on the cpci.ca website. Now we're going to talk about diaphragm design and code requirements from the National Building Code. So Clause 41815 requires diaphragms, collectors, chords, struts, and connections be designed so as not to yield, and design shall account for the shape of the diaphragm, including openings. So with respect to the National Building Code, provincial codes, and CSA A23.3, you may have to increase the forces that you're designing your diaphragm for based on the capacity of the seismic force resisting system. So if there's overstrength in your shear walls, you have to follow the applicable provisions in CSA A23.3 and the National Building Code to potentially amplify the forces that you're using for your diaphragm design to account for sort of the capacity of those shear walls or cores. And also those design forces need not exceed forces determined with RD R not equal to 1. The National Building Code and provincial codes also require that torsional effects be considered with a minimum eccentricity of 10% of the building dimension. So if we had a building with shear walls on both sides and the center of resistance is in the middle, and we said, well, the earthquake force is applied at the center of mass, which is in the middle, we would say, well, we really aren't generating any eccentricity or torsion there. We could maybe design to having no torsion, but the code requires we consider a minimum 10% of the building dimension for a torsion, just to account for accidental eccentricities, and knowing that even if you had intended the structure be completely symmetrical, there may be effects there that are causing unsymmetrical behavior. So basically the building code requires that we consider this 10% eccentricity, which would put a torsion on our building even if it was completely symmetrical as far as the lateral load resisting system goes and the alignment of the center of mass and center of resistance. In CSA A23.3, there's a requirement for RD2 and higher structures that the minimum area of reinforcement of 0.002 AG be provided in each direction. To satisfy this requirement, you would need concrete topping on hollow core with appropriate reinforcement. Untopped hollow core would not have reinforcement in both directions, so for an RD2 structure, that would not be compliant with this requirement. Also, additionally, have some reinforcement requirements that it not be spaced more than 5 times the slab thickness or 500 millimeters and be developed in tension for its specified yield strength. So a lot of precast structures are designed for RD 1.5, where this requirement would not be applicable, but for RD of 2 or higher structure, we would have to satisfy those requirements, which really means we can't use untopped hollow core for any structures with an RD larger than 1.5. They would not be compliant with that requirement in CSA A23.3. CSA A23.3 also requires the diameter of bars used in struts, ties, chords, and collector elements shall not exceed 1/6 of the minimum element dimension. All continuous reinforcement shall be anchored or spliced in accordance with Clause 12, and all reinforcement not contained within confinement reinforcement or buckling prevention ties shall have their anchorage and splice lengths increased by 50%, or for splices and laps be staggered. So again, that only applies to Clause 21.9 for the applicable RD structures. Cast in place concrete topping shall not be less than 50 millimeter thick. Generally, due to camber, you may require thicker topping than 50 millimeters, but again, that's up to the design engineer. Cast in place non-composite topping shall not be less than 65 millimeter thick, and the surface of previously hardened concrete shall be clean and intentionally roughened. That's just to get good bond with the concrete topping. Typical cast in place topping slabs on a precast floor or roof tend to have shrinkage cracks that are aligned with the joints between the precast members. Therefore, shear strength requirements for a topping slab diaphragm are based on shear friction. So I'll be mentioning that in the next few slides here. So if we had double T's or hollow core or precast elements and we have a cast in place topping on them, we know a weak point is potentially going to be developed over the joint between the precast concrete elements. So we would typically have a crack control joint, a tool joint in the topping slab matching the joints in the precast concrete elements. And for parking structures, that's a requirement in CSA S413. You are supposed to have joints in the concrete topping aligned with the precast joints. So when you look at the shear resistance equations in CSA A23.3, clause 2196, for that type of situation under the shear resistance, you see that there's no concrete contribution. It is basically based on the reinforcing or the shear friction across that joint, and you have a maximum permitted shear of 0.6 square root F prime C as shown in this equation. So basically the capacity in that topping is based on the reinforcement only. There's no concrete contribution. So that philosophy would apply to sort of a normal thickness concrete topping. This approach wouldn't necessarily apply where you have a very thick concrete slab on top of precast with double mats of reinforcing, you know, having reinforcing top and bottom, where it's unlikely that that crack in that huge thick slab over top of the precast would occur over the precast joints. But really this is intended for typical concrete toppings that are cast on top of precast elements such as hollow core and double T's, where you expect cracks to align with the precast joints. So what they're saying is use the reinforcement crossing that joint for the shear friction and look at that capacity in shear only. For a cast in place slab, the maximum shear stress limit goes up to 0.8. So you can see that from 0.6 for a concrete topping to 0.8 for monolithic concrete, they've decided to have different maximum limits there in A23.3. But again, if you were designing more of what I'd say a concrete reinforced slab over top of the hollow core, perhaps the monolithic concrete approach would be more applicable. So we've got hollow core slabs. We're going to have to look at, okay, if we're putting topping over them, is the top of the hollow core roughened for good bond? And then when we're putting topping in, we're going to have adequate reinforcement. Again, in this photo, construction is not fully completed yet. They'll have to chair the mesh up into the proper position and get the reinforcing placed in the proper location within the concrete topping. And again, need to watch out for, penetrations, and, they're obviously going to still go and place this potential cord reinforcement and the welded wire mesh as shear reinforcement on the floors over the hollow core in the topping before you cast the topping. But I just wanted to show some photos kind of in progress of how mesh and reinforcement is placed in concrete toppings to provide the diaphragm. So the parking garage code, CSA S413, requires that these crack control joints in bonded concrete toppings be located adjacent to all vertical surfaces over all joints between precast concrete components and other anticipated crack locations. Just a note here, they say in S413 that, you should tool those. I personally prefer tooling because if you're putting those joints in, that means the concrete is wet and it has not had a chance to dry out and start curing yet, where you could potentially start to get some shrinkage cracking, but it also does permit the bonded toppings to be saw cut. You have to do that early, as soon as you can, so that if you wait and let the concrete start hardening and shrinking, then you could get cracking before saw cuts are applied. But the S413 standard does permit saw cutting, but you need to worry about two things: making sure you don't delay with that saw cutting, and also don't cut down deep enough that you would cut your mesh. And then also S413 requires these joints be sealed with flexible joint sealant. Drain holes are to be provided within 150 millimeters at each end of hollow core, with a diameter of not less than 15 millimeters. And the ends of strands exposed on hollow core planks are supposed to be coated with a durable waterproofing material. Those are just specific requirements in S413 for hollow core. Due to the Northridge Earthquake in California in 1994, several lessons were learned. They noticed with some of the precast parking garages that with the cracking and some of the failure that occurred, that the joint between the precast elements and the topping was critical to the strength of how the diaphragm behaved. And low ductility welded wire mesh or cold drawn mesh was typically used in the diaphragm. So they, as a result of that earthquake, found that tight wire spacing on welded wire mesh did not have sufficient strain capacity. And as the cracks opened up, if you had a joint in your topping over top of the precast joints and the mesh was cold drawn, so it was slightly brittle and it was small, spacing of the mesh as far as the wire spacing goes, that did not perform well. And they researched that a lot and actually generated some changes in the American and Canadian design standard as a result of looking at the behavior of the cracking that occurred in the Northridge earthquake. So, thinking of the diaphragm as a large horizontal beam, typically we know, with concrete beams, we would be expecting to see diagonal cracks based on, the tension in the concrete and our theory of how shear works in a concrete beam. But what they saw was the cracks that developed followed, the straight lines, following the precast joints, not following kind of what you would expect from diagonal cracking on a concrete element that's experiencing distress and shear. And, definitely need to make sure that with precast construction, we're holding the whole structure together, and we don't want joint failure or failure of the concrete topping at the joints leading to partial collapse. So as a result of the Northridge earthquake, provisions were put in the ACI 318 code and then also in CSA A23.3 that if you're using welded wire mesh as reinforcement in your concrete topping, again for RD2 and higher structures, they want you to use a wide wire spacing. So say the spacing should not be less than 250 millimeters on center. Again, this is probably good for people walking on mesh on site. Using the wider spacing of the wires helps with potentially walking in the mesh anyway, so that could have some potential placing advantages. But the real reason it was done is due to the required elongation or strain with respect to using mesh for reinforcing. We know from structural theory that the strain is the change in length over the length, and if our wires, cross wires, are providing anchorage for the mesh wires, we know if we have a small length between wires, we would get a smaller strain or a smaller elongation, whereas if we have a large spacing between the cross wires that are providing anchorage, we would get a longer elongation and a higher strain. So basically, if we want to get more stretch, more elongation, we want to use a longer length between the anchorages. So that's what really developed from the Northridge earthquake was, well, we want a larger strain, we want a larger elongation, which means we need a longer length of wire stretching. So that's why the spacing of wires used in RD2 and higher structures is restricted to 250 millimeters or larger. And basically, you also still have to satisfy, your minimum temperature and shrinkage requirements. And I just wanted to note here too that even though I'm just showing one cross wire as far as the strain elongation goes per CSA A23.3, you need 2 cross wires to develop the yield strength of mesh. We also have to consider structural integrity requirements in CSA A23.3 clause 16. All structural elements shall be effectively tied together. So when we're doing a total precast building, we need to make sure we're tying all the elements properly together and satisfying the structural integrity requirements of the code. Back in 1968, there was an explosion in England in a 22-story precast concrete structure. I think the explosion happened on the 18th floor in the morning when a gas stove was lit to make some morning tea, and it caused an explosion, which then caused a progressive collapse. And as a result of that, pancaking in that particular part of the structure, provisions were carefully looked at in the Canadian CSA 23.3 to have, again, minimum requirements for tying structures together to provide structural integrity and hopefully prevent progressive collapse. So within clause 16.5, there's requirements for perimeter ties, which would be part of looking at the diaphragm design. So you would maybe design your diaphragm for the required forces, select your chord reinforcement and your collector reinforcement, and then just make sure that satisfies the structural integrity requirements as a minimum. And then just as far as tying all the precast elements together, you'll go through and look at longitudinal ties, transverse ties, and vertical ties. So these provisions apply to structures that are 3 or more stories in height. And again, requirements for structural integrity have some minimum design forces for the connections and the ties. So tension ties around the perimeter of each floor and roof within 1,500 millimeters of the edge shall provide a factored tensile resistance of not less than 60 kilonewtons. So we know, if we can develop the strength of 115 ambar, that's about 68 kilonewtons. So that gives you sort of the general magnitude as a minimum for structural integrity, but you still have to design your diaphragm for the required forces. This is just a check to make sure you satisfy these minimum provisions. Now we'll look at large openings and force paths. So when you have a diaphragm, and darn it, it's not a great, perfect, big, rigid, flat plate beam, we've needed to put an opening in it. Well, we need to now consider that with our structural design and properly engineer and design the diaphragm for the opening accordingly. So in this case, if we're looking at, a load being applied in this direction on the diaphragm, we're going to get compression developed in that zone. Section AA, and again, depending on how large that zone is. We may have to provide sort of I'll think of it as a column compression region within the diaphragm where you have potentially a small region subject to a large compression. So you're going to have to look at that. And if you need to confine the reinforcement and satisfying all the applicable provisions in CSAA 23.3 for your concrete design. So in this case, we have load being applied to a diaphragm with an opening. So we're going to have to design the diaphragm to accommodate the opening, follow our forces through with an appropriate load path, and design accordingly. So in this case, if our load is coming down, we know we're going to have potentially some compression struts and tension ties. And again, depending how the engineer is developing his model to examine the strength of this diaphragm, we may decide to use some type of truss approach where we're looking at transferring the forces through and then putting reinforcement in the regions where we get tension. And again, tension reinforcement around openings, if you're doing this type of approach where you've got fanned compression struts and tension regions, you really need to look at the strength of those zones and these nodal zones where the elements are coming together of tension and compression, and potentially extend your reinforcement well past the opening. I see some engineers just extend reinforcement, the development length past the opening without really looking at what's happening with the whole truss action. You need to look at, how the load from the compression is getting into the tension and how that is being transferred, kind of like a strut-and-tie node design. And you really need to, make sure you're extending your reinforcement into the anchored zones appropriately to transfer the forces. So that's very similar to just a design on a dap-dan beam or a corbel, that same type of approach where we're looking at some type of truss and we have to follow the forces through the various compression and tension elements of our model, and then the connection in the node regions, and again, just following the forces through. So that similar idealization or approach could be used when looking at discontinuities and openings in diaphragms. So this is a diaphragm with, a big notch out in the middle. And if I said, oh, if this was a beam, and let's think of the left and the right-hand side as supports subject to this uniform load, we'd know, wow, we're going to have to really look at that as a beam design and decide what our model is, how we're going to analyze it, how we're going to reinforce it, and accommodate that large penetration in the middle. So again, we need to carefully examine that and look at it. Again, think of diaphragms as beams and sit down and look at the shape and say, okay, if that was a beam supporting gravity load, ooh, I've got this big notch in the middle and my depth of beam changes. How am I going to reinforce that to make it work? And the same approach needs to be applied to diaphragms. Similarly, if you had a building in plan view looking like this, that would be a nasty beam to design if your support was on the left and the right. You'd have to look at how you're going to design that beam, how you're going to drag the forces to where you want them. Do you have tension reinforcement and shear reinforcement properly designed in the various regions of the beams? So again, you need to think of the diaphragm beams as a beam and just design appropriately. With respect to hollow core, quite often the perimeter of the building maybe is stepping in and out, and you can have some hollow core planks that are longer next to shorter ones. And potentially what can happen, again, depending if you're on footings or caissons and piles, if you had some differential settlement, in this case, we're saying that those longer planks that are sitting on a foundation wall on the outer edge maybe are experiencing some differential settlement compared to the foundations under the shorter planks there, that you would potentially get some cracking along the joint between the two. And that cracking seems somewhat intuitive, but I just wanted to explain what's happening there. So basically, if you see cracks, in joints between hollow core, or even in reflecting in the topping above the hollow core joint, okay, there's a tension happening there. Again, in this case, we kind of think, well, sort of makes sense, but why exactly is that crack happening? And I guess what happens, we use keyways on Hollowcore to really lock the planks together so that they won't move differentially, and we do that so that we can keep, you know, one plank from moving from another, so the whole floor kind of goes up and down monolithically. And the keyways that are grouted in provide this little compression strut, so as one slab wants to go down, it has to push on the other, and that works both ways, and they kind of are locked in so they'll move up and down together to share loads and deflect the same. However, if we have forced deformation where we say that right plank, I am moving you down because your support is settling, the only way it can move down is if it slides on that grouted keyway, and that diagonal portion of the grouted keyway as it slides would then make the hollow core plank move down, but that would also mean the joint is opening up. So basically what's happening is the forced vertical movement of one plank is actually causing a horizontal widening of the joint or cracking in the topping or the joint due to the vertical movement. So I just wanted to mention that, you know, even though it's a vertical movement, because it's sliding on the sloped keyway, it does create horizontal movement that then opens up with a horizontal crack in the flooring or the topping or the grout between the hollow core planks. So now we'll discuss a few lessons learned from structures in previous earthquakes. So diaphragms are an important part of the seismic resisting system, definitely require proper engineering effort, and the effects of floor diaphragms can be overlooked with simplifying assumptions, so you really need to do proper engineering of your diaphragms. Sometimes diaphragms have not performed well in earthquakes and have caused collapse of some precast concrete buildings, and even simple detailing enhancements can often really improve the seismic performance of a building. We mentioned earlier that, you know, the diaphragm is just one component of following the force path through from point of application of load down through the structure into the soil and foundations. And basically it's an integral part. We have to ensure that the structure performs well, the diaphragm performs well, the connections perform well. If, and obviously this is not a precast structure, but if we have failures during a seismic design and we lose part of the structure due to one link not being strong enough within our load path, then it doesn't do much good if certain parts remain and certain parts of the structures fail. We need to ensure we've looked at all the components and connections of our system and that there's no weak links. So again, just showing we don't want parts of our structures not being strong enough and having a weak link that would cause a large potential collapse to a portion of the structure while other portions remain. Several lessons were learned from the 2011 Christchurch earthquake in New Zealand with respect to the CTV building. Poor connections between floor and roof diaphragms and the vertical elements resulted in some big problems, as well as interstory deflection was too large. So really, even though this wasn't a precast concrete building, we'll look and discuss several of the principles. Need to make sure, you know, obviously your diaphragms are holding your building together. They're providing support and bracing your columns. So, you know, you can't lose your diaphragm, or you really need to make sure, you know, your connections are properly designed to take the required forces also. From observing the CTV building after the earthquake, it was noticed that rebar pullout failure occurred at levels 4 and 5, and that rebar wasn't even provided at the lower levels, which is obviously a construction problem. Also, it was noticed that joints between concrete pours and precast elements were not roughened. There was improper rebar placement throughout the building and lack of adequate rebar development along the shear wall. The CTV building definitely had an undesirable floor plan that we'll discuss, where the center of rigidity was really offset from the center of mass, and that had openings and this large eccentricity that really needed to be properly considered. So if we have a building where the center of mass, where we can think of the earthquake force being applied, is really offset from the center of resistance, where the shear walls are off to one side, we generate that large torsion. So for the CTV building, you know, the center of mass is kind of towards the center of the building, and the stair and shear wall core with elevator is off to one side as shown in yellow. So the center of rigidity, that resistance of that core, is way off to the right. Yet the center of mass with the earthquake load is acting more near the center of the building. So it's really dependent on that connection to the core. It's a highly eccentric building, and I guess twisting of the upper floors was witnessed in moments before the collapse. So here you really have to think as the engineer designing, how are you getting that whole shear from the earthquake on that diaphragm floor plate to the core wall? And you know, you have openings due to the elevator, you have openings due to the stairwells. If your main shear wall is the one to the right in this figure, way away from the building, how are you transferring those forces through sort of the landings in that area? How are you taking the diaphragm force from this large force plate and getting it to that far right wall? And then what are the resultant torsions going into the perpendicular walls? So that's a real complex load path there to try and take the earthquake force into the far right wall, you know, knowing that you have openings due to the elevators and the stairs and just a small section of floor landing that can get to that far right wall. So that's a very complex design. You also need to consider vertical irregularities, where maybe you have a multi-story building acting as a shear wall going all the way down to the foundation. And if you have a podium level or underground parking where those shear walls maybe are getting support from your diaphragm at the main floor level, which could change your structural design of your system. So again, is your diaphragm at that podium level or main floor level, is it going to resist and take the shear from the shear wall in the building above? If you have rigid, stiff connections and you're connecting it in, then it's going to want to transfer that force into your main floor diaphragm, and you'll have to design it appropriately, and that'll change the shear and the moments and your design of your shear wall, because now you have a very large reaction at that main floor or podium level that's taking shear out from the shear wall above, versus if that was not connected or had soft connections somehow and carried straight through down to the foundation, then it may be a cantilever going all the way down to the foundation level. But if you are providing support at those other diaphragms due to underground parking or some type of podium level, you need to consider that, because that puts a huge reaction potentially into that main floor diaphragm. So you need to look at the connections. Are you transferring load into that diaphragm? Are you not transferring load into that diaphragm? And make sure all the connections are suitably designed for how you are designing the structure to work. So with frame structures, you need to be careful if in a seismic event, if you have a building frame supporting hollow core and the frame is undergoing flexural movements and deformations, that the hollow core can go along with it. Otherwise, you could end up with very large cracks in the topping, just due to the deformations that the floor system had to undergo as a result of the moment frame from the beams and the columns that were supporting the hollow core system. You know, if they really need to bend and deform during an earthquake, and the design of the diaphragm, i.e. the concrete topping in conjunction with the hollow core, can't tolerate those deformations, then you know you could end up having problems with the reinforcing and the cracking in the concrete diaphragm. And certainly you don't want a hollow core plank falling due to inadequate support at one end either. So you need to make sure that you're really having proper bearings at the end of hollow core to accommodate any anticipated movement at the supports. And again, from the 2011 New Zealand earthquake, really need to be careful of the diaphragm and the connections of the diaphragm to the structure. In this particular case, there was some thinning of the diaphragm due to some architectural requirements, and that would have reduced the strength of the diaphragm and the connections. So you got to make sure, you know, you're coordinating with the architectural details and looking at what's happening during construction, and make sure that nothing is happening that's compromising your diaphragm design. So I'd like to thank a few people that assisted me with photographs that were included in today's webinar. Dominic Lemieux from PACO and Kurt Ruland from MTE Consultants. I'd also like to thank Sonia Sari from Chords Lab. Sonia passed away at the end of last year and was a long-term member of the CPCI Technical Committee and contributed significantly to the precast concrete industry. So this webinar is dedicated to the memory of Sonia Sari. Okay, that's the end of our webinar. I'm now going to answer some questions that were posted online. So one was a question about the sound transmission of Hollowcore. So that really wasn't covered in today's webinar, but if you go to the cpci.ca website, CPCI has done a significant amount of research at the National Research Council, the NRC, to show compliance to the newest building code requirements, you know, regarding ASTC ratings and that type of thing. And that research is posted on the website. And I know a new publication is coming out soon that would apply to total precast buildings and sound transmissions. So for that information, you can go to the cpci.ca website. Had a question here about the bowing of Hollowcore, which I'll interpret as the camber. So basically with any pre-stressed element such as Hollowcore, our pre-stressing force is applied near the bottom of the element to offset the tension near midspan of the member. So because we're pre-stressing offset from the centroid of the shape, we're naturally creating this upward camber, this upward deflection of the piece. So with Hollowcore, that's part of sort of the elements design of any pre-stressed element where the pre-stressing force is eccentric to the centroid. We're going to get that upward cambering. You can't really offset it. I mean, you could talk to local precasters that may have the capability of putting in some top strands in Hollowcore. That's fairly rare, but you know, as soon as you start to go and put strands in the top to offset camber, then that defeats the purpose of the bottom strands. So it's probably more important to prevent differential camber, and you can work with your local precast manufacturers and the design engineers to look at your particular situations with respect to trying to minimize camber. They may have other solutions or things that they can look at doing if camber is causing an issue, or you know, certainly trying to ensure Hollowcore planks that are side by side do not have large amounts of differential camber. Also had a question, should chords be within the diaphragm itself, or can they be included in the walls? So that question might have been asked before I showed a couple of those slides, but certainly you can have your chord reinforcement, you know, I'll say within the wall region of a diaphragm. And again, as long as a structural engineer, you're following your forces through, saying, okay, here's where my chord is. How is my force getting there? You know, you may have to look at shear friction and some other types of methods to ensure you're transferring your force from your Hollowcore to get to that chord. But yes, that can certainly be done. I had a question at stair openings, mechanical shaft elevator openings. Are they considered horizontal irregularities for rigid diaphragms? I would definitely say yes. I mean, any opening in a diaphragm is an irregularity. I guess you need to look at the size of that opening and effect on the design, and you know how big it is and where it's located, and you know, use your judgment whether that would be considered a horizontal irregularity for the building code requirements or not. Would you be able to accommodate slab depressions for different types of floor finishes, roof diaphragm and floor drains. So yes, you could certainly design a diaphragm to accommodate slab depressions, whether it's depressions in the topping, or if you're looking at something with staggering the hollow core with at different heights or something, and it all can be designed, and definitely can accommodate floor and roof drains and that type of thing. So certainly there's possibilities there to design diaphragms with depressions and openings and that type of thing. If you had a steel building with diagonal bracing, do you still need Hollowcore to take part in the lateral load resisting system? So I'll interpret that as a steel building, maybe with cross bracing. And I guess if it's Hollowcore that's providing the floors or the roof, your Hollowcore floor or roof system still has to transfer, the wind or seismic loads that are coming on the building from the walls and the floors to the steel elements that are maybe part of the lateral load resisting system. So I would say definitely that answer would be yes, the Hollowcore would still be part of the lateral load resisting system and still need to work as a diaphragm, unless in some type of structure you actually had a horizontal steel truss for the whole floor, and the Hollowcore was just put on top of that. But I probably think that wasn't the intent of your question. Several questions regarding seismic rehabilitation of precast diaphragms, both for Hollowcore and double T's. So yes, I would say diaphragms can certainly be strengthened and retrofitted seismically. Different options of, again, it all needs to be engineered, but going in and looking at, can you cut in and place some new reinforcement, or use, steel straps, or, potential fiber reinforced plastic FRP solutions and that type of thing. So I would say yes, diaphragms can definitely be rehabilitated to satisfy certain requirements. So I would say Hollowcore diaphragms and double T's, with the topping and stuff, certainly there's a possibility of doing seismic upgrades there. How to make sure sloped ramps don't participate in the diaphragm. So I guess that would be, related to a parking garage maybe, where you have a whole bay being on a slope. And, if it's a sloped floor, then, just like the diagonal braces I showed, it is going to become part of the system. If it's on a diagonal, it's going to potentially attract some lateral load, as a tension or compression member, compared to maybe your shear walls or other members of the lateral load resisting system. So, essentially you'd have to look at either disengaging it to not attract forces, or know that there's going to be loads going into it and design it accordingly. So I guess it really, your options are, you either have to, if you have a sloped member that's going to act as a brace and you don't want it to, you'd have to disengage it, or if it's there, you're going to have to know, well, the forces are going to go into it, and design appropriately. Had a question about the connection U-bar detail I showed. How do you grout the concrete in the U-bar photo? Does it completely fill that core? So yeah, that's a detail, again, used in Ontario. I think, probably considering shear friction with a bit of a hook on the bar, and concrete or grouting it in, whatever the engineer is doing there, he's probably analyzing it as a tension connection with a bit of hook development length, and would have to fill in that portion of the core and look at what the capacity is for that particular connection. And again, it's up to the precast engineers that are designing those, how they're designing it, if they're looking at it as a shear through the bar or tension friction, and where that load is going and how it's working as a connection, and does it have sufficient capacity. So certainly would want to fill it fully in that region of the U-bar, and again, that's all based on the engineer's design. For shear connections used to connect individual sections of large floor diaphragms, how do you calculate the number of connections needed and the spacing to ensure floor stiffness would transfer the shear as a single diaphragm using an untopped floor system? So again, I think I kind of showed the methodology there. Basically, you have to design for the force. Connections would have rated capacities that are engineered and be based on the spacing. So again, depending on the situation, you have to look at, okay, what is your design force for transferring load from the hollow core diaphragm into the shear core walls. Once you know the force, then you need to look at designing connections that work appropriately for those forces. And really out of that design, it would tell you, how many connections you need and what they're spaced at, and you just follow proper engineering procedures. If the connectors start to be too many and get closely spaced together, then that could have an effect on the capacity that you need to take into account. So again, it's just all proper engineering design. Is it possible to design a hollow core slab diaphragm with no topping and an RD of 2? So I guess in my opinion, I would say if you have hollow core as your diaphragm, you don't satisfy, and no topping, you don't satisfy the CSA A23.3 requirement of having reinforcement in both directions. So I would say untopped hollow core diaphragm would not comply with CSA A23.3 for an RD of 2 structure. I guess, if you had some alternate methods and means of showing that type of system could work with an RD2 structure and the building authority and everybody accepted, that there may be some potential solutions there. But I guess in answer to the specific question, I would just have to say that an RD2 structure with untopped hollow core would not comply with the CSA A23.3 requirements. For lateral load on the long side of a diaphragm, how can we calculate the shear force between the diaphragm and the long wall? So again, I think I kind of covered that earlier in the presentation. Basically, it all comes from the structural design with respect to looking at your loads, following your loads through, whether it's a rigid diaphragm, flexible diaphragm, semi-rigid, how is it getting to your shear walls, then what forces those reactions are, and just designing accordingly, whether you're looking at beam behavior or strut-and-tie behavior or shear panel connected behavior. It's all just comes from the engineering design. So that's all the time we have for answering the live questions today. I'd like to thank you for attending this CPCI webinar on hollow core diaphragms, and I hope you enjoyed the presentation. Thank you.